I'll talk more about it when we get there, and I'll try to.
And also, is our next meeting Saturday or Thursday?
I think I want to say Thursday's good.
You can get back to me on it.
Okay. So
Returns where we left off. Or...
yeah. Now there are more examples in the notes. Of various different algebras.
Mm-hmm.
And I'll let you read those, and we'll come back to them as we study more.
Alright.
But I told you about the null numbers. You could also talk about like the, null numbers of the form a plus b epsilon plus c epsilon squared, or epsilon cubed is 0.
Yep.
You can look at like sort of higher null numbers. And then there's other things that are a little more exotic, where you've got two generators and they interact in some way, and things like that. But let's see. So I wanted to try to focus here for the next little segment just on a calculus itself, which is like the rules of calculus over an algebra, right?
Mm-hmm.
And so, definition, if you have a function which goes from the algebra to the algebra again, then f is differentiable. I should say a differentiable at p in a if f is r differentiable. Oh, wait a minute, did I say that? Oh, no, I did not say that. Sorry.
You hit record, right?
You
hit record.
Oh, that's a good question. Yeah, it's blinking. That is a good question to ask.
No,
Given the last hour. So it's a differentiable at p if there exists dp f element of Ra. Now here Ra is equal to the right a linear maps on a, we talked about that before, right?
Mm-hmm.
So for example, left multiplication by a number is a right a linear map. But more than that, such that the limit as h goes to 0 of f of p plus h minus f of p minus dp f of h divided by norm h is equal to 0.
I mean, I'll take the definition of derivative almost.
Right. So, in fact, it is essentially the definition of, it's essentially the definition of real differentiable, except the definition of a map being real differentiable, or sometimes people will say Fouché differentiable. Right? Fouché differentiability does not impose this condition on the differential that we have right a linearity. That's like a super strong extra bit of algebra. But it is, of course, the case that if a mapping is, I'm trying to find my blue marker. I just lost my blue marker. Oh well. So theorem 5.5, as I call it. And again, we're in the introduction to calculus paper still. If f is a differentiable at p, then f is r differentiable at p. So. And I'll just call that r differentiable. So r differentiable also would be called Fouché differentiable in the current context. Now the reason, of course, we can't, just use a difference quotient is because, well, we can't generally divide by a vector. And that's still true in algebra, Although some people do, and I'll talk more about that in this paper. Let's see here. So the proof is just that this is the Frechet quotient satisfied, and if it is right alinear, then it's automatically just R linear. So an example of a function which is not a differentiable, and this kind of ties into a later discussion, so I'll mention it here. But if we have V1 is the identity, right? And then you have V2, Vn, and an invertible basis. Invertible basis for A, all right? Then if we have zeta equal to, x1 plus x2 v2 plus da 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 plus xn vn. All right, so this is the algebra variable essentially the algebra variable is zeta. The underlying real variables are x1 through xn, right? So every algebra variable is, in some sense, a way of packaging n real variables in a very specific way. And so, as I discuss later, you can then define conjugates, like zeta 2 conjugate, which is going to be, x1 minus x2 v2 plus da 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 plus x and vn. Or you could just write this as equal to zeta minus, 2x2 v2 for what it's worth. But, right, and indeed, there's more of these, right? You can factor all the way on to zeta bar n minus 1, which is equal to x1 plus x2 v2 plus xn minus 1, vn minus 1, minus xn vn. Right? So these are the n minus 1 conjugate variables that we can define for an algebra. Now in n equals 2, we just have the one conjugate variable, like you've seen in complex a little bit. Right? So I'm not sure how much I really want to talk about that with you here, so let me just do it all now and get it out of the way. We may or may not come back to this, kind of depends on what direction our research goes. But let's see here. So remember I showed you how to define like partial z and partial z bar formally?
Nah.
We have like partial. I found formulas for, I found formulas for x1, for x and y in terms of z and z bar. And then I figured out like,
For z and z bar.
I'm not sure which day I did this. Here, a quick sidebar. If we have z is x plus iy, right? And we have z bar is x minus iy, then this gives us that z plus z bar is
2x.
2x, right? And z minus z bar is 2iy, right? And also, so we can divide by 2, right?
Mm-hmm.
Alright, so formally, partial z is like partial x, partial z, good grief, partial z, partial x, good grief. Partial x, partial z, partial x plus partial y, partial z, partial y, right? But now this is, again, and as I told you, this is kind of like not legitimate. This is formal, quote unquote, formal mathematics because this is not really a chain rule. I'm just giving you a heuristic for how I remember the rule actually. And so partial x, partial z would seem to be a half, partial y, partial z would seem to be 1 over 2i, which is minus I over 2. So that's 1/2 partial x minus I partial y, right? So this calculation I knew from complex variables, I decided to generalize.
Okay.
Now this concept of setting up these n-1 conjugate variables, it's due to, see here, I'll tell you. It is due, stupid double scrolling. I'll just take it too far. Come on. So we're gonna stop that. I found it in. Let's see here. I believe. I'm not sure which one of these it is, but it's either. It's probably the 2012 paper by Maria Armenta, Gonzalez, and Romero on solving system of autonomous ordinary differential equations by reduction of a variable of an algebra. This is reference 16 in my A-CReqns paper. But anyway, so
I found it. There it is.
yeah, so I think that's where I found these conjugate variables. But so they define the conjugate variables the same way I just did. All right.
Mm-hmm.
But what they didn't do was define the they didn't define the partial derivatives with respect to the conjugate variables in quite the same way I did. Similar, but a little bit different.
Is this when you derive the Laplacian?
Yes, I used this to see that the Laplacian was partial z bar.
Yeah.
Which is partial x squared plus partial y squared times like 4 or something, or times 1/4.
Yeah, 1/4. There you go. Okay.
So see here, like in order to make this formal calculation go,
Mm-hmm.
in the original complex case, I had to solve for x or y, and then sort of proceed formally, right?
Yeah.
So and it's kind of circular, all right? But once you make this, so basically you make this your definition, and then you can go back and prove, for example, you can prove that like partial z is 1, and partial z is 0. All right, these things you can once you make this your definition for partial z. Because if you think about hitting x plus iy onto here, for example, feed it x plus iy, what happens? That gives you 1.
Yep. And that gives you I.
That gives you I. So you get 1
Minus
minus I squared,
Yeah.
which is
Oh,
2.
yeah.
2 over 2, 1. Okay.
And then you get 1. Oh, and then to get 0, you get 1. Okay.
And-
1 minus 1, 0. Yeah.
Alright. So,
With you.
okay, but actually that was sort of my internal logic to write down this formula. But anyway. So, I need to like mimic this to come up with the corresponding thing for that, right?
Yeah.
And so what I did was, like, the first order of business is to solve these equations for the real variables. So how would you solve, those for the real variables?
To solve for partial z or zeta.
Yeah, like how do I solve this for x? I mean, this is,
Everything has an x term, pull an x out. Oh no, they're different x terms.
so I think it's kind of easiest to see, and like, so see that?
Yeah.
This gives us, if you look at that, that gives us 2x2 v2 equals to zeta minus zeta bar 2, right?
Yeah.
And actually the same is true for generally j. And that's for j equals 2, 3, all the way on up to n minus 1. Right?
Yes.
So you can solve that. You solve that, you get, and this is why it's important for this is where it's important for us to have an invertible basis. See, because to solve for xj, I have to know that I can multiply by the inverse of that. This is a real variable. The vj is an algebra. It's an algebra element. It's a number, an a number. So this is like 1/2. You could write 1 over 2 vj with the understanding that that's 1/2 times vj inverse if you want. I'll just write 1/2 vj inverse times zeta minus zeta bar j. And then that's true for j equals to 2 to n minus 1, right? How about x1?
We're solving for x1.
x1 is equal to what? x1 is equal to
Let's just
zeta
plug it in, yeah.
minus what? The sum j equals 2 to n minus 1, or 2 to n rather.
Yeah, and of v n.
Mm-hmm. Xn v, right?
Yeah.
But of course, you can see that you can take this right here
And plug it in.
and plug it in right. Yeah, plug it in right there.
Wait, but that's xn, not xj.
Right. I have to change the. I shouldn't use n there either. That should be j. Oh no, this should be n.
That should be n.
That was a
Yeah.
mistake. That was a mistake. Sorry about that.
No, but now I'm with you now.
So, fine.
So yeah, you plug that in.
Right. So you get like your zeta minus the sum j equals 2 to n. That can't be 2 to n minus 1, right?
Well no, you're going out to vn.
Okay, careful here. Oh, I'm a dummy. This actually does. I started it at 2, so this does go to n.
So yeah.
Sorry. Counting.
Zeta.
So j equals 2 to n, and you got yourself 1/2 vj inverse z minus, zeta minus zeta bar j, and but of vj, right?
Yep.
So of course, in the context that the algebra is commutative, and I haven't been super careful about which goes where, but let's assume that A is commutative, okay? Well, let's assume, because I haven't been that careful about non-commutative issues here, assume A commutative. Because I haven't been super critical about which is on the left and which is on the right, okay? But anyway, if that's the case, of course, this and the inverse cancel, right?
Yeah, and then you're left with 1/2 zeta. Oh, does that mean you could probably pull out a zeta?
Well, that means that x1 is equal to,
The sum of 1/2 the sum. Yeah.
and yeah, you're right. We could work that out, couldn't we? How many zetas do we have?
Out to n zeta, or well, it'd be 2.
And minus one of them, right?
Yeah.
So what we got here is we've got 1 minus n minus 1 over 2 zeta. That's from this term and these guys. And then plus the sum j equals 2 to n of, the minus and minus gives me plus, so just find 1/2 z bar j, I think. So
did we not pull out that 1/2 with the zeta?
well, like it goes to both terms.
Oh, you're right.
So I'm actually skipping ahead to section 6 here at the moment, just for the sake of containing this discussion. I mean, in other words, I'm chasing the rabbit. Okay. And so the calculations I'm outlining at the moment are encapsulated in it's, ooh, dang. So look, I'm looking at equation 70. And somehow I have a 3 minus n times zeta there. There's a half. Oh, what happens if we simplify? If we pull the half out of this, what happens? 2?
Yeah.
Minus n, minus and minus 1, so it's 3 minus n. So this expression is not at odds. It's a different way of writing my equation 70.
You pull the 1/2 out, so that would be. Well, you also pulled that 1/2 out.
Right. So what I'm saying is I could write this as 1/2 3 minus n zeta plus the sum j equals 2 to n of zeta bar j. I can just pull a half out.
1 sec. 1/2. So the n 1/2, and that'd give you n plus 2 divided, and then you took a 1/2 out of that, which you 2 over 2 and 3. Yeah. Okay.
All right. Now again, this does not prove what I'm about to write, but it motivates my definition. This was my motivation for making these definitions, was to go through the same formal calculus that works for complex. So that formal calculus is solve for the real variables and then, write down what's partial, like partial zeta. It should be something like the sum j equals 1 to n, of partial xj partial zeta. partial xj. So that's partial x1, partial zeta, partial x1, and then, sum j equals 2 to n, partial xj, partial zeta, and I've broken it up into those two pieces because those two pieces are qualitatively different, right? The formula for x1 stands in contrast to all the others. And so like when I look at x1, right, what do I get? Partial x, see this down here? x1 equal to over here. So I say that means I should put 3 minus n over 2 times partial x1. And then how about the xj? Well, it's the xj up here. Right? So what's this? Just 1 over 1/2 of Vj inverse, right? And so again, this is a formal calculation. This actually is my definition for what I mean by partial zeta.
Okay, you're showing things.
Now to save room, I'm just going to write this one down directly.
Okay, I'm just checking things. So 3 1/2, yeah, and then pull the 1/2 back in there. So when you're subbing partial x1, partial zeta, when you take the partial of that? Oh, you are? No, wait, no.
I'm taking partial x1, partial zeta with the assumption that I just can look at the coefficient of zeta, and that's going to be that partial derivative. That's the formula. That's the formality here. It's that's again, this is not a derivation. This is just a sort of a heuristic argument to show you where my definition. I'm being honest with you. This is where my definition came from.
Okay.
For these partial derivatives, because, and what I will soon show, or maybe I won't show, but I'll tell you, is that partial zeta of a differentiable function, it is naturally tied in with what I mean by like the derivative of an a differentiable function. So I'm making a distinction between, it's like in complex analysis, you can define f prime of z by the difference quotient.
Mm.
And that f prime of z you could distinguish from, say, partial f partial z, where partial f partial z was viewed in terms of the underlying real partial derivatives of partial x and partial y.
Yeah.
And it turns out that the derivative from the difference quotient and the partial f partial z are the same thing with the correct identification made. And it turns out that partial f partial zeta is the same thing as the dpf at the start with the correct identifications made, which I haven't quite explained yet. But let me get this over with here. And so this one, when I look at the partial derivative with respect to 1, with respect to zeta bar, see what happens? You just get 1/2. So you get 1/2 partial x1. I'm working off the idea that partial zeta bar k partial zeta bar j is conjugate alpha kj. Okay, so that's why I only pick up one thing from that sum in the x1. All right. I just get that one thing, which gives me the half there. And then also, I've got k equals 2 to n, right? And so then I'm looking at this here. So for k equals 2, think of j being k, taking the derivative with respect to zeta bar. So I pick up the 1/2 z k inverse.
Yeah, you drop the zeta term and then you keep everything that's in front of the zj.
So it's almost the same as the previous one. I said instead of having a plus, I get a minus 1/2 v k inverse partial ovj inverse rather. Partial x j there. All right.
What was that? Wait, what was that the conjugation?
Oh, sorry. I just wrote down. Well, let me just say that actually was a. Let me just double check on this. So this is my equation 71 and equation 72 on page 26 of the Introduction to Calculus. In fact, this is exactly what I've written there. All right. And so I would point out that you can agree or disagree, you can critique these calculations, whatever. It doesn't really matter to me because at the end of the day, these are definitions for me. All right, this right here, definition. This is how I define my derivatives with respect to the algebra variables, all right? Now that I've made those definitions, and we've defined the n-1 conjugate variables, I can state a theorem, which is a straightforward thing to verify a theorem. Partial zeta, 1, partial zeta bar j, 0. Partial zeta bar j, partial, and here I'm writing it down now. Zeta bar k is what I just erased.
Oh, okay.
But now it's a theorem, not a heuristic. Because these assertions can be checked by doing nothing more than taking the necessary real partial derivatives of the conjugate variables against these vector value differential operators. Let's just do one of those calculations to make sure that I'm not just, what's the word? Bloviating. Sorry. Don't mean to sound like Bill O'Reilly. No one wants to sound like that. That's right, I said it.
I don't think a lot of people know who Bill O'Reilly is in my generation. I just know that we're going live.
This is the no spin zone. Let's see here. I don't really care for him anyway. Too much of a I don't know. What was the advice we learned from Forrest Gump?
Life's like a box of chocolates.
More bread you have, less crap you have to take. No, not that one. Mom always said, if you don't have anything good, something like, if you don't have anything good to say, don't say anything. I say so.
I learned from Forrest Gump is don't date Jennies.
Don't date Jennies?
Yeah.
Yeah, it's been a while since I've seen that movie. All I really remember is that I would rather rewatch that movie than that other horrible dumpster fire movie where he talks to a coconut for 3 hours.
Wilson.
Oh my goodness, I hate that movie so much. I hate that movie.
Forrest Gump, I actually really enjoy that movie. I can't get over the fact that's an AIDS baby. Is that bad?
An AIDS baby?
Yeah, she had AIDS. That's what she dies of.
Oh. Hmm.
And like people are like, well, she got it after. I'm just like, nah. Big assumption. Huh?
Yeah, I don't know.
You see, like, I'm not going crazy here.
So what happens here? Let's kind of. Most things are 0, right? Like
Yeah.
partial x1 hits everything here. This one, it's 0 on all of this, right?
So, yeah, 0, and then.
So we got like 1/2 partial x1, right? Which of course is 1, but I'm just writing it down.
Yeah, that's 1.
That term. Now what happens with this term?
Wait. What? So isn't that our zeta bar? Zeta bar j?
No, but we're letting this act on all this, right?
Oh, yeah.
So this, by the way, this term, I'm missing a sum, aren't I? Yeah, this has got a sum. Goodness gracious, that's got a sum. J equals 2 to n. Sorry about that. Oopsie. Yeah.
So that x partial xj is gonna.
Got minus. Oh, goodness gracious. What am I doing at the moment? What? I'm a dummy. This is, you're right. Oh, fine. You know what? Let me not do that. Let me fix this here. I'm so sorry. I can't follow my own instructions. What? This is not partial. You're telling me that's partial zeta bar j, right?
Yeah.
You're right. It was. Right. And so what happens here is that it only cares, like this is only, that's 0, right?
Yeah.
And also this is mostly 0, except where this gets what? The
j term.
Right, the j term. So we get like minus 1/2 vj inverse, partial xj, right?
Mm-hmm.
Vj.
But we're commutative.
Yeah, we're commutative. This is 1.
Yeah.
This is 1. So we get 1/2 minus 1/2.
0.
0. Right. Which is indeed part of what I claimed in the theorem, right?
Yes.
But that was not the interesting part. So, dang it, now I gotta do more. Partial zeta. So that was supposed to be 3 minus n over 2, right? Partial x1 plus the sum j equals 2 to n minus 1, or not n minus 1, n, sorry. 1/2 vj inverse partial xj, and we're letting that act on zeta, which of course is x1 plus x2 v2 plus xn vn, right?
Mm-hmm.
So of course the first term picks up just 3 minus n over 2.
Yeah.
And then think about how the next term works. Well, the next term,
It's gonna hit all the j's.
yeah, it hits everything, right?
Yeah.
But every one, like when it hits 2, it gives you like partial x2, which is 1, and then it gives you v2 inverse times v2, which is 1, so it gives you like a half.
Okay.
So each one of these gets a half. A half plus a half plus a half plus a half plus a half,
Okay.
right?
So just a sum
1/2, and how many of those are there?
j. Oh, 2, right?
Well, if j went from 1 to n, it'd be n,
Oh, yeah.
but there's 2 to n, so it's n minus 1 to n. Right?
Yeah.
The n's cancel, right? Because you get minus n over 2 and plus n over 2, those
Yeah.
cancel, and you're left with 3/2 minus 1/2, also known as
1.
1. So that's why partial zeta is 1. Now, in the paper that I referenced, and again, I'm indebted to them because I don't think I would have thought of this without what they did. They had a different definition for their partial derivatives such that it didn't work out like this. Their conjugate variables were not, I would say my conjugate variables are genuinely independent. That's what this theorem essentially says, is that the conjugate algebra variables are independent with respect to this calculus. And theirs weren't, and the reason for that was they had a different definition for partial zeta.
What was theirs?
I don't remember, but it wasn't this, and it made this thing work out a little bit different. It had a dimensional dependence.
Okay.
Which was neat. I mean, it worked out, theirs worked out so that partial zeta and partial zeta bar were genuinely independent only in n equal to 2, which is kind of cool. But anyway, I like these. And then, okay, so great. Now I've defined these. And then
that makes sense. The last one makes sense why it's either only 1 or 0 depending on if they're equal or not.
right, that's what
Yeah,
you want.
if they're equal, they go out to 1. If they're not equal, that goes 0.
Exactly. And I keep double scrolling. I hit 2-finger scrolling, and like it's just you think I'd learn. And then where my cursor is versus where the arrow is, Alright, so this is my theorem. My theorem 6.4 also has one other thing, which is if you have partial zeta bar j partial zeta, that's 0 as well. And the proof, I have 3 equations, 74 through 77. Alright. And so theorem All right, I have to talk about theorem 6.5. So my apologies. Right now we're down in the weeds of explaining different ways to think about the Cauchy-Riemann equations.
Yeah, I read that from that first paragraph.
Which is not bad. It's just not where I was trying to go to. My original intent for today was not to do this, but here we are. Okay, so. Oh man, a mess.
Is C given a constant ij to the k, like this Cijk? It's just a constant.
Those are the structure constants.
Yeah.
So they're usually just 0 or 1 for most of the examples I've shown you.
Yeah.
-1, but in general they could be more interesting. So those were the numbers that define the multiplication with respect to your choice of basis. So I'll remind you. So definition, we have vi star vj is equal to the sum over I j k from 1 to n of c I j k bk. Here we're assuming that A is the span over the reals of v1 through vn. So these are the so-called structure constants. So theorem 6.5 says that we can characterize a differentiability in terms of, oh man, I put the k up here, didn't I?
Yeah, you did. That's
Well, so this, yeah, sorry about that. So Cijk is Cijk.
that was just I think a formatting thing.
Yeah, I mean different. I'm stuck between worlds. I'm reading papers from 1940, 1930. They're all down. The indices are all down.
Mm-hmm.
Whereas when I look at stuff that's more modern, they tend to put the index up because of other considerations. But in any event, so we're supposed to say if ff is a differentiable of p, right?
Now you're talking about 6.5.
Yeah, theorem 6.5. All right, so let's look at the proof. Partial f, partial f, partial xi, star vj. All right. What's that equal to?
The sum of k of the constant.
Uh,
Wait, no, you're
so-
talking about 2. Sorry.
Yeah, you're fine. So this, okay, so just to start with, we got to go through some. See, this is where skipping sections ahead of my paper hurts us a little bit. But I have defined what I mean by partial f, partial xi with respect to a basis. So partial f, partial xi is really just notation, in some sense, for dp f of vi. Now really the only, I mean to be honest with you, A-CReqns, the only partial derivative that you've ever really dealt with before has probably just been the partial derivative that you see in Calculus 3, right?
Yeah.
Or in my differential geometry course, where even there we weren't really dealing with partial derivatives defined with respect to a non-standard basis. See, this v1 through vn doesn't have to be the standard basis. All right?
Yeah.
But I would,
If it's not, wouldn't everything just kind of go to 0?
no, I'm just, this is essentially my definition. If vi is any basis, then I define coordinates with respect to that basis by, x1 through xn.
Mm-hmm.
Then the derivative with respect to that coordinate is defined to be the differential on the corresponding basis.
Okay. Yeah. Then, yeah. I'm with
So
you.
it coincides with what you already know,
Mm-hmm.
and it's a natural way to define partial derivatives with respect to variables, which are not just Cartesian variables. Anyway, now we have, of course, now we know what the differential is right linear, right?
Yeah.
So we pull that in. And then definition of structure constant, right? This is the sum ijk of ci, I guess I'll put my k upstairs to be annoying, vk. You can, whichever.
I get why you put it up top, because you're really just talking. That one's just talking about the number of the vector, rather than like the.
Yeah, each index plays a different role, for
Yeah.
sure. That third index it does feel like it has a different role than the other two, yeah. But when people just looked at equations and didn't think about bases so much, the sort of the equivocation of the different indices made more sense back then, in some sense. Or maybe they just were more averse to writing indices up. I don't know. Anyway, so there. Now, this is linear. These are real numbers.
Mm-hmm.
So you pull out,
Yeah.
And then you're left with dpf
No VK.
vk, which is partial f partial xk.
Is that because of how you define the
Yeah, definition.
Yeah.
Partial f partial xk is dp f of vk.
Yeah.
This is at p technically, you know. So there you go. Sum over ijk of c I j. I'll write the k down because I want to be different. And annoying partial f partial x xk. And that was item numero uno in theorem 6.5. No,
Yeah, gotcha.
this, I think this ends up actually being somewhat important to the research that I've been doing with Elliott. Like, when we've done a fair amount that directly looks at structure constants, and so like if you want Kosher-Riemann equations, which are directly in terms of Kosher structure constants, here you go. This is your jam. Yes. So because these are Kosher-Riemann equations is what they are. But in terms of structure constants. Now, the next up is given that we have a basis such that the first thing is the identity. Then we actually, I think I proved this to you before, partial f partial xj is partial f partial x1 times vj. So like number 2 we looked at the previous time. I can go through it again if you want, but
No, I don't remember. Because you just defined it as, that's how you define derivative, is just the changing the basis to the first, that v1 being the partial
yeah,
of it, times all the other things.
yeah,
So like if the basis is like the identity is x1, then partial of the identity times v n plus 1 out.
yeah. Oh, I guess I need to do it here because we talked about it. Well, here, let's just try it. Partial f partial x. What was I just saying? Partial f partial. Oh, I want to do partial f partial x1 times vj, right?
Yeah.
And here, let's assume that v1 is equal to the identity.
Yeah.
All right, so I put 1 there. That puts a 1 here,
Well, that's the identity.
and this puts a 1 here, which makes this just equal to
Vj.
vj. We don't need the structure constants then, right? So that's just, yeah, that just becomes vj, which just becomes partial f partial xj, and there you go, that's 2. Cool. And often this is how I like to look at the Kosher-Riemann equations. Kosher-Riemann equations say that I can trade a j derivative, the derivative with respect to the jth variable, real variable, instead for the derivative with respect to the first real variable times vj. Now I can only do that, of course, if my basis
It's 1 on the
is
identity.
1 on the identity. And if I had the 1 is somewhere else, if like 1 is the jth one, I can still get away with this, right? But,
Yeah.
you know, it's more complicated when the identity is some kind of linear combination of your basis elements, then it's more annoying. Now 3, if you have a commutative algebra, then you can write these symmetric Kosher-Riemann equations.
And then this is from our definition of what this is. That's partial f partial xj.
Here, let's see. So let's try to work out 3. Let's just try to do it. So partial f partial xi times vj, right? Now we're now dropping the assumption that 1 is the identity.
Oh, okay.
We don't get that to play with now. So we go back to,
So we're,
this is that,
yeah, one more I below it.
which is that, right?
Yeah, but that would, well, if you just go off the linearity, it'd just be wouldn't it just be a,
We're assuming A is commutative, right?
yeah. Oh, then, wait, So it's not right, but it's only right alinear, right? It's still right alinear?
It's still right, yeah, I mean, that's the assumption of
So
A-differentiable.
If it was commutative, I would switch bi, bj,
Uh-huh.
take the derivative of bj, which would give you a partial over partial bj.
So that's,
Yeah.
yeah. How about this, right?
Times bi, yeah. And then take the partial of that to be, what's the definition say? df of partial xj
Right.
at p if you really want to.
Yeah, try to, yeah, right.
And then bi, yeah.
But see, there it is. This is equal to that. And of course you can, since it's commutative, you can finish the job here by vi times partial f partial xj, right?
Mm-hmm.
So I sometimes call these the symmetric Kosher-Riemann equations. These are pretty nice. If you want to derive some kind of general fact about an algebra where you don't know for sure that your identity is a basis element, these are not a nice next best. These are. I kind of prefer these to the one we found in number 1. Like structure constants are. I don't know. Just it feels very basic to get down to structure constants. I don't know, but they do play a role. So that's theorem 6.5. All right. Now, theorem 6.6 is a result in this paper, which I think I'm not unjustified in saying is new to my paper. And so theorem 6.6, are we good?
Yeah. So. So what we proved is that partial f xi, partial f partial xi times or star bj is also equal to partial is equal to partial f partial xj times star bi. Yeah.
Right, you see the i's,
Yeah. Just
the
they flip flop.
so
And equals the same thing.
so theorem 6.6 says that if a is differentiable, if f is a differentiable at p, then the differential of f at h is actually equal to. And we'll assume, let's let a be commutative, okay?
Okay.
I think I assume that there, but I'm going to assume that here. Then dpf of h is really, of course, dpf of, and commutative, and we're going to assume v1 is the identity, right? Then dpf of 1 is, of course, it's dpf of 1 times h, which is also partial f partial x1 of h. And although we haven't quite talked about this yet, so we'll see. Partial f partial zeta is df d zeta is what I call f prime of zeta. All right, we'll come back to that later, but that's one of the benefits here. And partial f partial zeta bar j is equal to 0 for j equal to 2, 3, all the way out to n. Now I think I can state a slightly stronger theorem. It's not just an if-then, all right? Like, if you're given a function which is differentiable in the real sense,